jumping back in here, let's talk about free energy and how it relates to equilibria. So when we're trying to find the Gibbs free energy of a reaction, and we're using that table from the appendix at the back of the book, that data is at standard conditions. And if you remember, standard conditions is 1 molar for anything that is in aqueous phase. It's 1 atmosphere for anything that's in gas phase. And it's a pure solid or liquid. And for most situations and most reactions that we look at, things are not going to be at exactly 1 molar in 1 atmosphere. If we're using a solid or a pure liquid, then those usually are just pure. But if we're looking at things that are in aqueous phase or things that are in the gas phase, they're usually not 1 molar or 1 atmosphere. Usually there's something else. Or at the very least, not everything involved in the reaction is at 1 molar in 1 atmosphere. Maybe we might have 1 or 2 things, but not everything. And for the Gibbs free energy value to be correct, given the numbers from that table, everything would have to be at standard conditions. And so because practically nothing that we do is completely at standard conditions, we need some way of finding the Gibbs free energy at those non-standard conditions. And we're going to find that using this equation right here. So this equation will allow us to find the Gibbs free energy value for any reaction at any non-standard state, as long as we know the standard Gibbs free energy, the temperature at which it's taking place, and then Q, which, if you remember, Q is the reaction quotient. So that is the same as the equilibrium constant, just not at equilibrium. So it is the product over the reactants, where we have the concentrations of these two things raised to their coefficients. So using the reaction quotient, we can find the non-standard Gibbs free energy. So we're going to do that here with this reaction. This says to consider the reaction. It's happening at 298 Kelvin, where we have 2 nitrogen monoxide reacting with O2 to form 2 nitrogen dioxide. And we're given the standard Gibbs free energy, thank goodness. We could find it ourselves if we needed to. We could go back to the table and plug the numbers in and everything, but they're giving us a break here with this one, and they should just give us the standard Gibbs free energy. And we're asked to find the non-standard Gibbs free energy under these conditions. Just to point out here, we know that this is the non-standard for a couple of reasons. Number one, because the pressures of the gases are not 1 atmosphere, and also because it's missing the little circle there, that little circle, the naught, that tells us that this is at standard conditions, and because this is missing the little naught, this is at non-standard conditions. And furthermore, we're asked to determine if the reaction is more or less spontaneous under these conditions than under standard conditions. So, given what we know from the last slide and the data from this slide, why don't you go ahead and pause the video and see if you can, number one, work out what the non-standard free energy is, and then also work out whether it is more or less spontaneous than at standard conditions. So pause the video now. All right. So if you remember from the previous slide, the non-standard Gibbs free energy is equal to the standard Gibbs free energy plus RT LNQ. That's this here from the previous slide. So we are just straight up given this, so we don't really need to do anything to find that. R is the same R that we've seen over and over again. So it is 8.314 joules per mole K, and we're going to use the joules version of the number here instead of the liter atmospheres version because we're dealing with energies. T is just given to us in the problem. It's 298 Kelvin. And so really the only thing that we need to kind of work out here is Q. So Q, if you remember from the previous slide there, is products over reactants. And we're going to raise their concentrations, or in this case their pressures, to their coefficients. So Q for this particular reaction is going to be the concentration of NO2, which is 2, raised to the second over, because that's our only product is that one, so that's the only thing in the numerator, over the concentration of NO, or in this case the pressure of NO, which is 0.1, raised to its coefficient, which is 2, times the concentration of O2 raised to its coefficient, which is just 1, and so you just can leave it with nothing there, and it's understood to be 1. So really this is actually 2 squared over 0.1 cubed, since we have essentially 3 0.1s in the denominator. If we go ahead and do the math for Q, that is going to be 4 divided by 0.1 raised to the 3, which is 4,000. So that is our value for Q. So at this point, we have everything we need. We can plug in our values. So delta G is equal to negative 71.2. And I think I'll change this one to joules. Joules, and actually I don't need to have any denominator there, it's just joules. And the reason I'm doing that is because we need the joules here to match up with the unit here. You could have switched this to be kilojoules. Either way is going to work out. I just decided to go with them both being joules this time. So we're going to have our R value, 8.314 joules per mole K. And then that will be times 298 K times the natural log of 4,000. Since that is Q, is 4,000. All right. So if we do our math here, so it's going to be negative 71.2 times 10 to the third plus 8.314 times 298 times the natural log of 4,000. That is going to work out to delta G at non-standard conditions is equal to, and I'm going to go ahead and convert this back into kilojoules. So it's going to be negative 50 point, we'll just call it 7 kilojoules. Okay. Or negative 50,650 joules. So that is the non-standard Gibbs free energy. If we compare that to the standard Gibbs free energy, this is for the second part here, where it asks us to determine if the reaction is more or less spontaneous. If you remember, negative Gibbs free energies are spontaneous. And not only that, the more negative it is, the more spontaneous it is. So this is negative, so it is spontaneous, but it is less negative than the standard Gibbs free energy. So the standard Gibbs free energy is negative 71 kilojoules. This is negative 50, essentially, kilojoules. So this is less negative, so this is actually less spontaneous. Than the standard conditions. It's still quite spontaneous, though. Like, you're not going to have any trouble getting this reaction to happen, but it will go even faster if it was at standard conditions. All right. We take this a step further, kind of building on top of that, if we're interested in how the Gibbs free energy value relates to chemical equilibria, if you remember Q, that equilibria or that reaction quotient, if your reaction is at equilibrium, Q is equal to K. Also, if you remember from earlier in this chapter, if you're at equilibrium, the non-standard Gibbs free energy is going to be equal to 0. So the delta G is 0 at equilibrium, and Q is equal to K at equilibrium. So if we take both of those identities, both of these things, and we plug them into this equation from the previous slide here, K is going to insert in here for Q, because again we're defining that we are at equilibrium, and delta G is going to be 0. And so that's what we've done here. Just plug in 0 there, plug K in instead of Q, do a little bit of rearranging, because while this is a correct equation, it's not in its most useful form. So you kind of move all of this stuff over to the other side here. Essentially subtract this from both sides so that it kind of flips over here. We get the standard Gibbs free energy value is equal to negative RT ln K. And even this is not the normal way that you see this equation. This is perfectly reasonable and perfectly usable, but usually the way you see it represented is like this, because most of the time what you're going to be looking for is that K value. So if you're trying to work out excuse me, what the equilibrium constant would be for a theoretical reaction that you're interested in running, you could go to a table, work out what the standard Gibbs free energy is, and plug in whatever temperature it is you want to use this at. Again, usually it's just going to be 25 C, which would be 298 K. Excuse me. Plug those into the equation here, and you can actually work out what the equilibrium constant is going to be. It's pretty nifty, actually. So, just to kind of give ourselves an idea of what kind of K values you get for a given Gibbs free energy value. If you had a reaction like the one that we just saw, where you have negative 50 is your kilojoules per mole, is your delta G value, that, even though, back here we're saying, this is less negative than it was at standard conditions, you might remember from just a couple seconds ago I said it's still quite spontaneous. Just to give you an idea of exactly how spontaneous it is, the equilibrium constant for this reaction is 5.8 times 10 to the 8. So it's essentially a billion times more. The numerator is a billion times larger than the denominator. And if you remember, that's products over reactants. So this part of the fraction is a billion times larger than this. You have a whole bunch more products than you have reactants. And this is at a not ginormous delta G value. 100, a negative 100 is quite a lot larger still, but there's quite a few reactions that you come across that will have negative 100 delta G values. That is 3 times 10 to the 17, which I don't even know what the number would be for that. It's, I don't know, several trillions or something like that. More products than reactants in terms of this ratio. So these are very, very spontaneous, highly product favored. I mean, at this point, at negative 100 delta G, negative 100 kilojoules for your delta G value, I wouldn't even qualify that as an equilibrium. Like, technically speaking, it is an equilibrium, but that is so incredibly product favored that personally, I would just be like, it goes to completion. There's practically no reactants there. Especially when you get up to the point where you have negative 200, it goes to completion. There's practically no reactants. And then the opposite is true here with the very positive delta G values. These are not going to move forward at all, which again, conversely means the reverse process is extremely highly favored. So if we take a look at an example here to try and find the equilibrium constant for a reaction, thankfully they gave us a fairly simple one here, so we don't have a whole lot of numbers to look up in our appendix. We are asked to use tabulated free energies of formation to calculate the equilibrium constant for this reaction at 298 K. So we're going to use this equation, and actually we'll use this form since we are just trying to find K. So K is going to be equal to E raised to the negative delta G over RT. So R, we always know that is 8.314. And I'm going to go ahead and convert this to kilojoules. Kilojoules per mole. K, sorry, I kind of ran out of space there. T, we're just given. It's 298 K. Delta G, we don't know yet. We're going to have to find that. So, if I look up those numbers in the appendix, it's probably going to be listed under nitrogen. All right. And this is going to be products minus reactants, which is going to be, we'll just do it this way. So we have one product. We have two of it. So NO2 in the gas phase. Let's see. Here's NO2 in the gas phase. 51.3. Sorry for my messy writing there. 51.3 kilojoules per mole. So those are our only products. Minus reactants. We only have one reactant, and that's N2O4. So N2O4, it is positive 97.5. Okay, so if we do that math, 2 times 51.3 minus 97.5, that gives us a delta G at standard conditions of 5.1 kilojoules. Okay, so now we have everything we need. So if we go ahead and plug in what we know, K is equal to E raised to a whole bunch of stuff, raised to the negative 5.1 kilojoules divided by 8.314 times 10 to the negative 3 kilojoules. And then the temperature is 298. All right. So, if we go ahead and plug that in here, E raised to the negative 5.1 divided by 8.314 times 10 to the negative 3 times 298. That gives us K is equal to 0.128. So, does that number make sense? Well, if we think about the value we got for delta G at our standard conditions here, excuse me, it's positive, which means that this process is not spontaneous. And so it would make sense then, if the process is not spontaneous, that K would be less than 1. Because what that tells us is we have, excuse me, we have more stuff as in the as reactants than we have products. Not very many products are being made, which means that it's probably correct that our K, it means that our K is most likely correct. Since the K tells us that we have more reactants than products, we're not making very many products, and delta G is telling us that the process is not spontaneous at standard conditions. And so it would make sense that if the process is not spontaneous at standard conditions, that we wouldn't be making very many products. So it's not something where you can absolutely tell that you have the correct number, but at least it makes sense. It makes sense to me that we would get a number less than 1 with a positive delta G value. All right, that is it for this chapter. If you have questions about this, we can talk about it in Blackboard Collaborate the next time we meet. Be sure to get the homework done fairly soon while it's fresh in your mind, and don't hesitate to shoot me an email as well if you need an answer faster than the next time we meet together. All right, good luck.